Log on, tune in, find out. Another good idea from Cambridge.
Second session of today, and I guess the last session today. And our first speaker is Krzysztof Patan from the University of Zielona, Góra in Poland, and he's going to speak, as it says, about group sensor scheduling for parameter estimation with in random effects distributed systems. So, thank you very much.
Thank you. So, as for introduction, to focus your attention, probably I should start with some examples from electrical engineering to introduce you to the field of distributed parameter systems. What is it really, and what design problems you can encounter during identification of such systems. So, very tangible first example is about electrical impedance computer-assisted tomography. Not quite popular in medical imaging, but quite popular in industrial applications. Here we have the pipeline with this is the two-flow example. Inside the pipeline, you have the oil and gas. So the question is how to reconstruct the interior of the pipeline based on the measurements taken with the measurement electrodes located at the boundary. Some of those electrodes are supply electrodes, so the electrical potential is supplied to the boundary, and other are just for measurement and gathering the data. So this is, as tomography is the two-phase process. So the first stage is to model the process. So on the left-hand side you have the image of the electrical potential. So the two supply electrodes deliver the voltage from the left and right side, and this is the reconstruction, so-called the forward problem of reconstruction, the modeling the distribution of the electrical potential. Then, based on the measurements taken on the boundary, we tried to reconstruct some electrical parameters within the interior. So, for example, the conductivity of the gas bubble and the oil are different, so we can build the image what is going inside the pipeline. So the problem is that the state of the system varies not only in space but also in time. So we have a pretty complex dynamics. So where the bubble of gas increases in size, the electrical field also follows the changes. So we have quite complex dependence of the state upon the spatial dimensions as well as time. As for mathematical modeling of this process, usually the distributed parameter systems, also called systems with spatio-temporal dynamics, are modeled using partial differential equations, sometimes integral equations, but the most common models belong to the class of partial differential equations. So in our example, it's like that we have the collection of partial differential equations which are dependent on the, in this case, on the conductivity coefficient, which has to be, it cannot be measured directly, it has to be reconstructed based on the measurement of the system state. We have the, within the areas contiguous to the supply electrodes, we have voltage, so we have the Dirichlet conditions and the Neumann conditions on other boundaries. The model, in a way, is a sophisticated one. However, in benefit of this difficulty to cope with such kind of models, we obtain very good accuracy of modeling, which can be used further in control, prediction, or modeling behavior, simple behavior of the system. The typical problem is if we have to reconstruct the unknown parameter of the system, so how to spatially, and of course we can go further, we can configure not only spatially but also where in space and time put the sensors, the measurement electrodes, in order to obtain as good as possible reconstruction of the unknown parameter. It may be even more difficult because it's not unusual. It's quite often it happens that the system is very sensitive to sampling. So as for second example, this example I've also used in the following to illustrate the algorithmic approach to design. So I will spend just 2 minutes to explain. The magnetic brake system is the idea of this device is pretty simple. In the simplest construction, it is a rotating plate made from conductive material, rotating within the magnetic field of the magnet. So the interaction of the magnetic field and rotating disk is like the magnetic field induces eddy currents within the disk. So it creates the resistance force, the torque, which breaks the disk. So it's a pretty popular device used in trains, in industry, but probably the most famous example of such magnetic brake system is the power electrical energy meters, which are responsible for our bills in almost every household. So maybe it's more complex, in construction, but the main idea remains the same. So the problem is that such magnetic systems are very vulnerable to sampling. What does it mean? So if I want to put some sensor somewhere here in order to measure the magnetic flux, the sensor of magnetic flux has the form of the coil. So it interacts in a way, it becomes quickly magnet itself. So every sensor became a magnet because of the interaction of the electromagnetic field. So it changes dramatically, sometimes dramatically, of course. It provides significant changes into the magnetic field. So probably the stories from the newspapers, how easy it is to cheat the electrical power meters using strong permanent magnets. Of course, it's not so easy because using strong permanent magnets you can spare some energy, but at least at your bill. However, such device is so vulnerable for magnetic field that you can easily destroy it. So it's easy to to reconstruct what happened to the device that you were using strong magnets to to increase the braking force in order to cheat with your energy bill. Okay. the interaction effect of magnetic fields of the measurement probes and device has deterministic character. However, it's so complex in modeling because it depends on many different factors, frequencies of input signals, temperature, material characteristics, and many other fluctuating factors that the real character of such sampling system and device is so complex that complex and obscure that a natural way is to rather not to try build a very good model, very I would say physical based model. The natural solution is to assume that the parameters can vary and can be treated as random variables. So when we are going to identify in the laboratory the system in order to give good models for use in the control and prediction, the question appears how to build a schedule where you are doing a test on the group of devices. They can vary not only upon the sampling sensitivity, but also by individual parameters coming from the technology of production. So the problem you can encounter are really, really complex. So summarizing those two examples, the subject of the talk is firstly answer the question how to determine the best configuration of the sensors all over the spatial area, and then to try to answer how to construct a good schedule for a series of tests on the individual units, individual devices, taking into account all the effects I was talking about. So, motivation stems directly from many tangible engineering applications. So there is a whole area which can be interested in the solution and construction of good designs, or at least methodology, how to try to improve the way of preparing the experiment. So finally, let's focus on what the class of systems is considered within this work. We assume that we consider the distributed parameter systems, which mathematically can be described by a collection of partial differential equations with some known structure. So the functions, the structure of the model is known and usually comes from physical considerations. The system depends on the vector, finite vector of unknown parameters, which according to many effects, individual distribution of parameters from device to device, and of course sensitivity to sampling, this vector of parameters is assumed to be a random vector, vector of random parameters. Sorry. This vector should be identified based on the observations which will be gathered from the series of tests on the individual devices, individual units. So for each unit we can take a different number of observations spatially located in some area where the measurements will be most informative. They provide a useful, useful data. Of course, if we've got and potential locations where to put the sensor, why we don't use the whole array at once? Once, because too much measurements can really decrease the performance of the device. So we introduce this interaction I was talking about. So it's not a good idea to do too much measurements in this case. And of course, to spare the resources, because using too many measurements transducers may be simply costly. So from device to device, we can change the locations of measurements, and I believe that this factor should provide some increase in the quality of parameter estimates. So from the statistical point of view, the statistical model, if the y is response calculated based on the PDEs, we come up with such random effect model. So the epsilon is a measurement noise, which is assumed to be white Gaussian in this case. It's in practice, it's impossible to obtain such kind of noise, but in the literature of such systems, it's treated as a very good approximation of the real. So we can live with such assumption. But anyway, because of the vulnerability of the system to sampling and changes in individual properties, we have to assume that the parameters are random variables following some distribution H, which may be, pretty complex. So further, we made the strong but important assumption that we assume that the observations are independent. So in fact, with such setting, the random effect model is not mixed effect models at all, but it's not because of we want to make the problem trivial. It's not like this, because probably it's the only way to cope with the complexity I will show within a few minutes, that we encounter a huge dimensionality of the problem, and what I'm talking about is to provide an algorithmic solution for large-scale problems, not for very simple examples. So further, we have the strong evidence from real data that still, with such assumption, we can achieve a good quality of identification process. So for engineers, it's this satisfactory criterion is really important. So as for construction of the experimental design, how we understand this. So for each individual unit, we assume that we take some measurements at different distinct spatial locations. It may be it is simple, because probably it would be nice to generalize this to the case where the measurements can be repeated at some spatial positions, but it doesn't change a lot the approach. So it can be easily generalized for such a case. As at the second level, when we repeat the test on different experimental units, the group design will be just a collection of spatial configurations of measurements taken for each unit individual. So roughly, our design problem can be formulated as determine the group design so as to maximize the identification accuracy. So the approach within the area of control, there are 3 different approaches, but probably the mainstream is the methods originating from the optimum experimental design. So I want to spend too much time on describing the alternative approaches. Based on the Kramer-Rao inequality, we can quantify the accuracy of the parameters using the efficient information matrix. Owing to this strong assumption of independent observations, we have this property of additivity of the information matrices from individual spatial locations. It helps a little bit, but not much really, because still we have to cope with numerical determination of the elements of this efficient information matrix. So probably this is familiar to everybody, that for small number of parameters, the most reliable still is the numerical integration, extensive numerically, but most accurate probably. Still, if the number of parameters is large, probably the numerical integration is hopeless. So tomorrow will be a whole session how to approximate properly using some stochastic methods, Monte Carlo approaches, and linearization, and so on. So we can more formally write down the problem as determination of the group design in order to minimize some measure operating on the Fisher information matrix. We have to put additional assumptions because the solution otherwise will be unbounded. We have to put the constraint that the maximum number of measurements is limited. So typical approach will be to use one of the most popular criteria from the literature, so I don't spend too much time on this. The design is good, but in engineering it's not the only purpose of the experiment, never. So the identification, is important, but usually we have to look into another things. The one of this is the cost of the experiment. Okay. So a typical problem related to the cost of the experiment is how to build a proper coverage, because the spatially variable system is not a good idea to provide the clusterization of the measurements within just in one location, even if this from statistical point of view is very beneficial. We have to deploy the sensors in order to provide the knowledge from the whole area, not only from this one local site. In the wider spectrum of applications within the wider context of the so-called wireless sensor networks, the coverage problem is strictly related to the communication. So each sensor has special range, and every sensor has to stay within the range of at least one another sensor in order to communicate properly with the others. So there is a lot of interpretation of this coverage problem. Defining the coverage matrix, which takes it's a binary matrix which takes the value 1 if some interesting subdomain lies within the range of the sensor and 0 otherwise. With such simple binary matrix, we can build the minimal coverage problem as the problem of maximizing some minimizing some maximal cost per each experimental unit This cost may be, in the simplest way, the number of sensors. So the number of sensors is probably the simplest criterion here. So we minimize the number of sensors used in order to provide the proper coverage of the whole area. So going further, also very important problem is proposed so-called balanced operation scheduling. I know that the word balance is very precious for the people from the community, but in engineering it means that what we want to have is just using the same amount, probably, if possible, the same amount of resources on each experimental unit. So this is balance in this sense. So the problem probably it's very easy to define. We just have to minimize the maximal number of resources, in this case sensors, used per each unit. This will provide the proper preparation of the. It's easier to practically to set up the experiment when you use the same amount of the resources every time. Combining all this together, we come up with extremely difficult multi-objective design problems. We have to simultaneously maximize the accuracy, minimize the resources, and minimize the usage of the resources, and fulfill the coverage constraints. So in fact, this is a multi-objective binary programming problem, which is itself NP-hard. It's really a huge space of search, even for simple problems. For example, when you have 200 prospective sites.
Right, press more heavily, please. That's very ill. Right.
Okay. When you have 200 sites and you probably want to use, let's say, 50 sensors per each individual unit, and you have at least 10 units, so the space is about of this order. So even if you calculate every second a new solution, so probably you should spend a few billion years on calculating or searching the full space. So even for not large numbers, we quickly obtain a large-scale problem. So it's not really to propose something to cope with this. Fortunately, there exist some techniques, some combinatorial approaches to at least try. Okay, one of them is classical optimization technique called branch and bound, which is nothing else as the searching for the along the graph of solutions, binary tree of solutions, and of course, probably I skip this. The idea is quite simple. So we have the initial problem, and we branch this problem. So we build the two sets. The set I0, which assume that some of the variables are fixed and take the value 0. The second set, I1, consists the variables, the indices of the variables which are fixed at the level 1. So fixing at the first stage just one variable to be 0 or 1, we obtain two alternative solutions. So we can follow in this manner further. However, if we be able to calculate the upper and lower bounds for the actual solution at each node, it is easily to prune the whole branches, so the not promising the solutions are discarded as whole branches of the search area. So the really key problem is to propose a good bounding procedure. So this is the key problem. So the branch and bound is classical technique, and in order to implement it efficiently, you need the very good procedure for building the bounding, building the determining the bounds. Sorry. So as I said, at each tree node, we relax the problem. So we relax the binary variable and assume that some of the variables not belonging to the fixed set of zeros and ones, some variables can be continuous within the interval from 0 to 1. So we try to solve the continuous version of the problem. In order to propose the synthesis of the whole, in this case, 3 criteria, each nonlinear, we have to use another technique, which is called goal attainment. It's one of the possible techniques to cope with the multi-objective optimization. It consists in application of the concept of so-called Pareto optimal solution. So the solution when you cannot increase the value of the one criterion without decrease in the value of the another. So for each criteria, we have to fix some satisfactory level. Usually, this value is the optimal solution in the case where I forgot about the other criteria. So I solve the problem with one objective function, and the solution is the satisfactory level psi k. Also, this goal attainment technique is very flexible because we have some additional parameters to tune up what we want to focus on. So those are just proportion. If I'm interested more in one criterion, less in another, I can tune with those additional weights. So this slide is for further, for the purpose of later use. It's just to show that we have a lot of constraints. Finally, using goal attainment formulation, we come up with the problem of only one criterion, one objective function, but at the cost of the many constraints. Okay. So solving this problem constitutes the very efficient way of determination of the upper bound. So for searching, just to show the results within just a few minutes. Going back to the magnetic brake systems, which can be modeled using some Maxwell equations, in this case even simpler version of the Lorentz equation, when we have the electrical conductivity and magnetic permeability, so those two parameters describing the properties of the material. What we are focused in this problem is to how to reconstruct the electrical conductivity of the disk, because it's not homogeneous on the whole area. The system dynamics, I will show probably how it looks like. So the permanent magnet operates on the rotating disk. The eddy currents are induced, and this is the picture of the magnetic field in time. So after, maybe once more. So starting with high speed, the eddy currents provides the braking torque, and after some time the disk stops. This is the dynamics, so the angular velocity from the initial one just going to 0, and of course the braking torque, which is greatest at the beginning, so the more speed you have, the greater torque is. And probably this is most important. This setup is, we put attention into the balanced scheduling and put attention into the accuracy with the same proportion, and paying no attention into the coverage. So we can forget just for a minute about the clusterization of the measurements. So for different values of the magnetic flux of the permanent magnet, and so the second parameter, and the first is the angular velocity, initial angular velocity. For each unit, for each test, we obtain a pattern, which is pretty intuitive, because the most important things, as you have seen from the dynamics of the system, happens within the area of the permanent magnet, which provides the braking force.
So the positions are with respect to the magnet, not with respect to the rotating plate.
Exactly.
Global position, right? Global position.
And here we provide the similar solution, but this time we also want to deploy the sensors in a different way in order to avoid the clusterization. Clusterization is, of course, the effect of this assumption of independent observation. So in order to put attention to this, we can obtain with the same algorithm within a couple of minutes. It's really effective, from this point of view. We provide a proper distribution of the sensors. Still, you can see that most of the observations focus on the area where something interesting happened, I would say. However, this time, some of the sensors has to follow strictly different pattern in order to measure in some other spatial areas. Okay, so thank you for giving me the extending the time. So probably I finished at this moment.
Yes.
I have one question and one concern. My question is that you basically deal with the inverse problem. And in case of inverse problems, since you reconstruct the image of conductivity and permeability, you end up with large number of parameters. So basically you have sigma and mu at each domain location. So how you solve this problem? Usually people do regularization. Do you use something like this?
Exactly. Another thing that is that for the design purpose, I don't have to solve the inverse problem, in fact. So the question is that, for example, in the impedance tomography, the approach is strictly different than usually in the computer-assisted tomography, that we always parameterize the space. So we base on the model. So this model has never have too much parameters. So this is the assumption. For the industrial purpose, it's enough. Of course, for some medical imaging, as you said, the so-called pixel approach. So in order to have a good resolution, we have to increase the number of parameters, not just a few, hundreds, thousands even. So here it's rather, those examples are based that the number of the parameters never will be very large. You have a large amount of the design variables, but the model is rather simple in this.
Second question or concern is that you assume that your parameters are random, but you don't randomly choose your locations. So in your case, it is if you choose the location of sensors, it is completely defined by the physics. So you can write down Maxwell equations and solve the system. So it's not sampling as we do when we consider random parameter cases.
Yes, indeed. So probably there is a way of generalization in such direction. So we can treat also a design variables as random variables and try to build some more robust with respect to the model uncertainty. And so, yeah, it's like you said. In this case, I'm assuming at least that the model approximates fairly enough the behavior of the system, and it really happens because the partial differential equations are flexible enough to really, with a few parameters, to provide maybe not the real picture of the behavior of the system, but fair enough to go further to the application.
That is a problem with partial differential equations. With two parameters, your problem still can be ill-conditioned, even if you have 5 observations or
Yes.
500 observations. It still can be ill-conditioned. It's by joint comment.
Yeah.
Yeah. So it will be great if you show your model and just give a couple of hints how you really introduce parameterization, just to understand where regularization came from. Because otherwise it's ill-conditioned problem and you need Tiffany's, whatever, regularization to solve it. At least what you draw, or what was on your slide, it looks like it's very tough problem in this sense. So it's a very ill-conditioned problem.
Yeah.
But can you come to the slide where this problem was formulated? I mean, no problem. Just to show, just give a hint how you did it. It was even different. Whatever problem you define.
I'm not sure what you are
Pick
talking
up,
about because oh yeah, so yeah, I skipped this probably. Here's the answer that I assume that some polynomial model of the conductivity of the disk here. So we have in fact 3 parameters which depend in some simple way.
So it's symmetrical case. Spherical, in your case, cylindrical case.
Yes, it is, but the disk only is, the parameter of the disk are symmetrical, but the magnet itself introduced the problem itself is not symmetrical at all. So, yeah, of course, this is the example which not pretends to be real application, because this is the example you can solve using the on-shelf PC. So within a couple of minutes. So when I parallelize the problem and use the computer cluster, the number of those, so this parameterization may be far more
And you can
complex.
prove that it will be unique solution if you solve inverse problem for, I have.
For the design purpose, I'm not solving it. This is important. I'm not solving the inverse problem for the purpose of design. So
You have to solve. Otherwise, how you derive derivatives of information? I mean, how you derive derivative and then build information network. That's what I'm trying to understand.
the derivatives, you solve the forward problem to have the sensitivities. I don't catch.
Okay, we can check.
Yeah, because
Okay,
really.
moment. You declare that one of the constraints that the alpha parameters should sum to 1, but you are choosing their values, you're not optimizing them.
Yes, indeed. So the choice is based upon some experience, or what do you prefer to do first? Are you focused on the accuracy of the parameters, or rather interested in some other aspects? However, you can optimize those parameters as well. But what would be the sense of such going random for what happens. I don't know. The interpretation of such optimization of those alphas would be rather difficult.
Well, thank you once again.